Swayam Prabha. Digital India. Educated India.
Now, I am going to talk about Gaussian distribution, which you have already talked at great length in one full module. Gaussian distributions are very fundamental, and I have computed various moments, conditional mean, and various quantities of interest related to Gaussian distribution. So, here I am trying to recall, let x be a random vector in D, m is mean, sigma. The sigma belongs to R d by d. That means sigma is a covariance matrix of size d by d. We say a random variable x is normally distributed to the mean, and covariance sigma is to say the functional form of the distribution is given by this 1 over 2 to the power of d by 2 square root of the determinant of sigma exponential, then the quadratic form, negative of 1/2 of x minus m transpose sigma inverse x minus m. We have already alluded to, so this should not be new to any one of you, Gaussian distribution in multi-dimension. You have to be able to manipulate this, understand this, analyze the properties of these distributions. When sigma is equal to sigma square I, then that implies sigma inverse is equal to 1 over sigma square times I identity. So, in that case, this quadratic term decouples, and I am putting m is equal to 0. So, this is a special case, m is 0 and sigma is equal to sigma square I, the little sigma square I. That means the matrix, the covariance matrix or diagonal matrix, all the diagonal elements are the same, equal to sigma square, off diagonal elements are 0. In that case, you can verify that this essentially is the product of n univariate Gaussian distribution. That means if the random variables are uncorrelated, it is independent. That is one of the unique properties of Gaussian random variables. Using this, now I can ask you to compute. So, x is random, x has a norm, it is a norm square. If x is random, norm square is random. So, I would like to be able to compute the expected value of the square of the norm of x. In this particular case, they are independent, there are d components, they are independent. No, this is not n, this must be d, sorry, this must be d. So, they are independent, each one are identical. So, that is essentially d times E of x1 square. E of x1 square, please go back, variance of x1 is equal to E of x1 square minus E of x1 whole square. E of x1 is 0 because I am assuming mean 0. So, this is equal to E of x1 square. E of x1 square is equal to variance, and that is equal to sigma square. Therefore, expected value of the square of the norm of x is simply d times sigma square, and that can be easily calculated. All this follows essentially because my xi's are IID, they are all from 0 mean sigma square standard 0 mean and sigma square as the variance. So, for large D, so now let us look at this now. For large D, the random variable square of the norm of x is concentrated around its mean. What is its mean? The mean of the square of the norm of x is d sigma square, and that essentially comes from law of large numbers. So, this is a result that should convince you that if you generate random vectors whose components are uncorrelated from a Gaussian distribution, the square of the length of the or the square of the norm of x grows as d times sigma square is fixed. So, the square of the norm increases as d linearly in d. Therefore, it makes sense to define square root of times d times sigma, the square root of this quantity, which is sigma times square root of d, that is called the radius of Gaussian. That is called the radius of Gaussian. I want you to think of this radius concept now. If I am in one dimension, I can draw the Gaussian like this. If I am in two dimension, please understand this is x, this is y. So, there is a bell shaped curve that is sitting around sitting on the top of this. And how do I explain that bell shaped curve? Yes, you can do a 3D plot, but one of the easy ways is to draw contours. Contours are locus of probability surfaces with a constant probability. So, this is the contour plot. So, what does this tell you? If you try to imagine a contour plot for the random variable norm of x square, you can readily see the contour plot for norm of x square. The expected value is going to be centered around d times sigma square. So, this you can do a very nice simulation. You can make d is equal to 100. You can compute one 100 dimensional Gaussian random vector IID with 0 mean unit variance or variance sigma square if need be. Then you compute x, from there you compute one number norm of x square. So, you got one number. Repeat this, let us say 10,000 times. Again you are going to get the distribution, and you draw the histogram of this distribution. It turns out that this distribution is not spread over a longer interval, it is going to be concentrated around the mean. The mean is d times sigma square, the mean is d times sigma square. Therefore, sigma times square root of d is by definition called the radius of the Gaussian. Now, I am going to talk about, so we talked about the behavior of the square of the norm of random vectors. We talked about pairwise distances between pair of random vectors. As d becomes larger and larger, these become the behavior of these objects becomes different, counterintuitive to what we are used to in 2D, 3D and so on. Now, to bring another facet of the discussion, I am going to consider what is called the tail probability. For example, I am sorry, this must be a smoother curve. This must be a smoother curve. This is the curve of normal 0, 1. Normal 0, 1. I am now going to pick A is equal to 1, A is equal to minus 1. I am going to ask myself what is the amount of, what is the area under the curve between minus 1 and plus 1. So, I am considering RA is the integral of the standard Gaussian between minus a to plus a. That means, it is the total probability mass contained under the curve between the points minus a and plus a. So, when a is 1, it can be shown that this is 0.683. So 68% of the total mass, please understand, the total mass is unity. 68% of the total mass is now contained within -1 and +1. So the tail contains, what is the tail? Outside in this area, that is called the tail. Outside the interval -a plus a. So if a is 2, it is 0.955, the tail is 0.045. If a is 3, it is 0.997, the tail probability is 0.003. So now you can readily see, even though the distribution has to officially go from -infinity to +infinity, 99.7% of the total mass is contained between -3 and +3. That means the tails are very thin. The tails are very thin. The amount of probability measure that is in the tail becomes smaller and smaller as A becomes larger and larger. Now, I am going to show you the computation of the tail probability. So, the whole thing in here for D is equal to 1, the standard one dimensional distribution. Now, I am going to talk about the tail probability of normal distribution in D dimensional space. So, probability that lies outside the sphere of radius 2. What is the sphere of radius 2? Please understand, sphere of radius 2, in the case of 1D, it is interval -1 +1. So, what is a sphere in 1D is simply a line -1 to +1. What is a sphere in 2D? That is a real sphere. So, I can think of in the 2-dimensional space, there is the sphere becomes a circle. In the 3-dimensional space, the sphere is a sphere centered at the origin. So, in the 3-dimensional space, the probability is distributed over the whole space 3 dimension. I am going to consider a sphere of radius 1, I am sorry, a sphere of radius 2, just for the sake of illustration, centered at the origin, which is the mean of the normal distribution in RD. So, now I am going to compute the probability that lies outside. So, that is called the tail probability. Please understand, in the case of 1D, the tail probabilities decrease as A increases, as you would expect. So, here I fix the radius, that means you can think of it as -2 to +2. So, as D increases from 1 to 5, 10, 20, 100, the probability that lies outside, this must be, I am sorry, that is an error here, this may be O's, the probability, oh I am sorry, this is right, there is nothing wrong here, okay. That means, sorry, the probability that outside is 0.04, as D becomes more, the probability outside becomes more, as D becomes more, the probability outside more. So, what happens? As the dimension increases, more and more of the probability moves to the tails from the center. So, if one way to imagine this is that if I have the distribution like this, as D increases, it is as though somebody is trying to push so that the mass oozes out to the tails. In 10 dimension, 94% of the probability mass is outside -2 sphere of radius 2. In 100, almost 100% of the total probability mass lies outside. But still, the maximum of the function is attained at x is equal to 0. Look at this now. Here is a function whose maximum is attained at x is equal to 0 because mean is 0. Even though the maximum occurs at x is equal to 0, as D becomes larger and larger and larger, you do not find any probability mass at the center. That means empty space is created. Almost all the probabilities have escaped to the tail. I think this is an important phenomenon. So, for large D, the tail has more information. Wherever there is probability, there is more information. It can be shown if you consider N0, N0I, what is I? I is the the covariance matrix. The probability of unit normal distribution in D dimension is contained in a thin annular space around x square is equal to D, and that should not be surprising. We already saw E of x square is equal to D times sigma square, but in this case sigma square is 1, so this will be D. So the expected value is D. If the expected value is D, what happens in here? Everything is getting centered around, the distribution getting centered around that D. And how do we state that in terms of probability measure? If you consider an annulus, please understand, so the square root of the norm of x is equal to square root of D. Norm of x is the radius. So if you consider a radius, what is that? If you consider a radius of square root of D, and if you consider plus or minus epsilon, the width of this thing is epsilon, is in this case is beta. So square root of D plus beta, square root of D minus beta. I hope you are getting a feel for that. So what does this tell you? This essentially tells you, if you consider a sphere of radius square root of D, and if you consider a thin shell around it, the probability mass lies in this symmetric shell around this radius of square root of D. So look at this now. The probability that the square of the norm of x lies in between square root of D plus beta and square root of D minus beta is greater than or equal to, that means it is at least 1 minus 3 times e to the power of alpha times beta square, where alpha is a constant, beta is something less than square root of D, e to the power of minus alpha is greater than 0, beta is greater than 0, but beta square is greater than 0, e to the power of large negative number is very low. Therefore, with a large probability, most of the probability mass is contained in a small annulus centered around the radius square root of D. Centered around the radius square root of D. So that's a very nice way to look at the behavior of Gaussian distribution. Now I am going to come back to another result, which is called chi-square distribution. I am trying to introduce lots of things. I introduced the notion of what is called gamma function. Now I am introducing the notion of what is called chi-square distribution. So what is the idea here? If x is a random vector whose components are IID, the square of the norm of that is a random variable. That random variable inherits a distribution, that is what is called chi-square distribution. Please understand, every random variable has a unique distribution describing it. So x is r to the power of k, x is a k-dimensional variable, xi's are IID random between 0 and with normal with 0 mean and unit variance. That means x is a vector all of whose components are normally distributed with 0 mean and unit variance. Y is equal to x square, which is the square of the norm of x. Square of the norm of x is equal to summation of xi square. It is a sum of k independent identically distributed random variables. Please understand, there is a general theorem. If x is normally distributed, x square is going to be chi-square distributed. Chi-square distributed. Please understand, x normal distributor can take positive negative value, x square cannot take positive negative value. So, if x is a single random variable, x square the chi-square variable which are 1 degree of freedom, here there are k degrees of freedom. The functional form of the chi-square distribution is given by this function. The distribution of capital Y is given by 1 over 2 to the power of k by 2 gamma k by 2 y to the power of k by 2 minus 1 e to the power of minus y by 2. This is called chi-square distribution. It can be shown this chi-square distribution has a mean equal to k and variance is equal to 2k. You should know, a data scientist should know many of these results. These are interesting results about transformations of random variables, interesting results relating to transformations of random variables. So x is a random vector, xi's are normal 0 1, I'm sorry, normal 0 1, xi's are normal 0 1, and summation of xi square is the square of the norm of x. Now, I would like to talk about the norm of x itself, which is equal to summation xi square, the square root of that. That means z is a new random variable which is equal to the norm of x. Please understand, y is the square of the norm, z is the norm of x. So, y is x square. So, if the square of the norm is said to be distributed according to chi-square, the norm is said to be distributed according to chi distribution. So, I am trying to introduce two new distributions, normal, chi-square, chi. Chi-square for the square of the length of the normal vector, chi is the length of the vector itself. The functional form of chi distribution is given in here. I want you to know, in probability theory is a standard exercise. If x is a random variable whose density function is p of x, if y is a random variable which is a function of f of x, what is the distribution of p of y? X p of x is given, f is given. So, I would like to be able to compute the probability density function for the new transformed variable. So, if the random variable get transformed by in a particular way, how does its distribution gets transformed? So, x to x square, normal to chi square, if you take the square root of chi square, it has become chi. The chi square distribution is given by 15, the chi distribution is given by 17. It can be shown the mean of the chi distribution is given by square root of 2 gamma of k by 2 plus 1 divided by gamma of k by 2, and the variance of z is k minus mu square, where k is the degrees of freedom. These are exercises in probability theory, multidimensional probability theory. Now, I would like to be able to concentrate on the distribution of the properties of the norm of x. We are going to talk about the concentration of the norm of x. Setting n is equal to k plus 1, simply a change in, it is simply a change in parameter. This here n refers to the dimension of the random vector. The expected value of x, look at this now, this is the random vector, and this random vector has a chi distribution. The random vector has a dimension n, sorry, the random vector has a dimension n. The n is parameterized as k plus 1. So, it can be shown the expected value of the norm of x is square root of n minus 1 times 1 minus 1 over 4n. it can also be shown that the variance of this is n minus 1 by 2n, which is roughly half. Now, I would like to be able to plot or calculate the values of the expected value of the variance as a function of k. K plus 1 is n, right? So, k n. Using this I can compute the expected value, using this I can compute the variance. Now, look at this, something funny happens, very interesting happens. The expected value changes, increases with n, and you would expect that. The length of the vector with a larger component must be longer than the length of the vector with the smaller number of components. But the number of components are random, and they are all uniformly distributed in the standard normal 0, 1. But look at the variance. The variance gets stabilized. It's all about 0.5. So, from the formula 19 you now know the variance is slightly less than half, but gets stabilized. Now, think of it now. I have a random variable whose mean is increasing, but variance is constant. If the variance is constant means what? The spread remains the same. So, whether you are trying to talk about a random variable in dimension 50 or dimension 500, while the mean are different. So, for 50 the mean may be here, for 500 the mean may be here, so this may be 22.35, this could be 7.106, but the spread, generally we see the spread to be like this, right? The spread remains the same. That means even though this curve, the distribution of the norm of x moves to the right because the mean moves to the right, the spread does not increase as a result of the dimension. So, whatever be the dimension beyond a particular point, you now know the spread remains constant. That means the value of x are concentrated around the mean value, whatever be the mean value. Of course, the mean changes with the dimension. Now, I would like to talk about two application problems about the impact of high dimension in statistics. This is called linear discriminant analysis. Linear discriminant analysis means what? I have, this is again population based analysis. That means population based analysis means I know everything theoretical. I know the distributions, I am going to be able to compute everything. So, consider a distribution normal mu1 sigma, mu2 sigma. That means I have two normal distributions with the same covariance, but differing mean. I am going to sample. When I get the sample from the mixture, what is that? With a probability B1, the sample comes from P1. With a probability P2, the sample comes from P2. P1 is greater than 0, P1 plus P2 is equal to 1. So, look at this now. There are two boxes, one with mu1, another with mu2. I am going to get one with the probability P1, I am going to get with the probability P2, but I am going to see an x. This x could come from this box with a mean mu1 with a probability P1. This x could come from this box with a mean mu2 with a probability P2. No one tells me where this x came from. I would like to be able to identify with a very high probability what is the distribution from which this x was sampled from. So, there are two Gaussian distributions with the same covariance, differing mean. X is a d-dimensional random variable. The mixer has a distribution which is p of x, which is p1 of x, p2 times p2 of x, p1 plus p2 is equal to 1. So, you got the idea here. So, the whole black box is a mixer. So, what is the standard algorithm to be able to identify whether x came from box 1 or box 2? The standard algorithm, okay, this is what is called signal detection problem. So, you can think of lots of scenarios. Mu 2 is greater than mu 1. So, if it comes from P 2, it is signal plus noise. If it comes from C 1, that is essentially noise. That is one way to look at it. So, we know P 2, P 1 because we know we are talking about population analysis. I am going to consider the ratio, which is the log of P 2 by P 1. When P 2 is Gaussian, P 1 is Gaussian, by substituting the normal functional form for P 2 and normal functional form for P 1 and taking the logarithm, you can readily verify that this L is given by psi of x. Look at this now. Mu 2 is known, mu 1 is, these are constants, sigma inverse because they are common, x is the random variable that gets out, mu 1 plus mu 2 by 2. So, this is the inner product of this vector, this is the vector, this is the matrix. So, inner product of two vectors, that is 20. Please understand, when I want to estimate, when I want to classify, I need an estimator. The estimator is also called statistic. So, this is the statistic function. So, given x, given all the parameters, I need to decide whether it comes from P 1 or P 2. This statistic is linear in x. Now, I would like to be able to make an optimal decision. I would like to be able to make an optimal decision based on the thresholding of psi of x. So, what is that we are going to say? If the value of psi of x is greater than some quantity, we say it is going to come from P 2. If it is less than some quantity, we say it is going to come from P 1. So, to illustrate that, we are going to now assume mu 1 is 1, mu 2 is minus 1. One is plus 1, another is minus 1. So, in this case, t is equal to 0 is a good threshold. Please understand, this is 0, this is minus 1, this is plus 1. So, if anything, if the value of psi of x is greater than 0, it is quite likely it came from P 2. If the value of this thing less than 0, quite likely it came from P 1. So, this is P 2, this is P 1. Of course, there is a small probability that x could have come from P 1 and be larger than 0. X could have a very small probability that it came from P 2 and less than 0. So, they are called wrong classification. If indeed P 2, if indeed x came from P 2, that is quite likely it is greater than 0 because the probability mass of P 2 is more towards the right of 0. The probability mass of P 1 is more towards the left of 0. So, intuition tells you that t is equal to 0 is a good threshold using which I can classify. A given x is from P 2, if psi of x is greater than 0, the given x is from P 1 if psi of x is less than 0. So, we have already seen there is a probability for error. So, to compute the probability of error, I am going to assume P 1 is equal to P 2 is equal to half. Hey, that is a tough case. They are equally likely to come from P 1 or P 2. The error of psi is P 2, it is less than, psi prime is less than 0. This is P 1, psi prime greater than 0. So, please understand, if it is greater than 0, it could have, with a larger probability it will come from P 2, smaller probability will come from P 1. So, when greater than 0, when it came from P 1, that is an error. Where less than 0, but when it came from P 2, these are called the errors. So, this probability and this probability errors, I am going to define the error to be 1/2 of the errors of the two types. when it came from P1, I say it's P2. So psi of x greater than 0 means what? It's quite likely it's from P2, but I say it's from P1, and so on. So x prime and x double prime are chosen from P1x and P2x. So the error in xi is given by this formula. Please, I am not going to derive this formula. These are standard formulas derived in detection theory in electrical engineering. So this is an integral, is an incomplete integral, a Gaussian integral. I am going to, you all know, if I have Gaussian integral, if this is A, what is the probability that it is less, x is equal to less than A? We generally denote it by phi of A. What is phi of A? Phi of A is simply 1 over square root of 2 pi integral from minus infinity to A of exponential minus x squared by 2 dx. That is the integral over from minus infinity to plus A, and that is exactly this interval. That is exactly this interval. And what is r square? What is r? R is given by r square. R square is, this is the vector, this is the matrix, this is the vector, and there is a transpose in here that is missing in here, sorry. So this is the quadratic function, mu1 minus mu2 transpose sigma inverse mu1 minus mu2, that is a Mahalanobis distance. Please understand that is a, we had called it as the energy. This is also called the generalized measure of norm. Do you remember? X transpose Ax, we call it the energy norm square. So you can think of this as square of the distance. So the square of the distance, that distance is called Mahalanobis distance, named after a famous Indian statistician who invented this concept of distances for using in decision problems. Now, more often than not, I do not know the distribution. I have to work with samples, just like in PCA, we are going to talk about a sample counterpart. We do not know the distributions. We are given a set of samples from P1, we are given a set of samples from P2. So that is the information that is given to you. We are given a set of samples from P1, we are given a set of samples from P2. I need to be able to learn the discriminant function, that it helps you to discriminate between whether it came from P2 or P1. The sample mean is mu1 hat, which is given by this. The sample mean, which is given by mu2 hat. I can compute the pooled covariance, the covariance of the object coming from class 1, covariance of the object coming from class 2. These are unbiased estimates of the sample covariance. Why this is sample covariance? This is a column vector, a row, that is an output product. These are matrices. So the sample covariance is a sum of the covariances of samples from class 1 and class 2. Class 1 means P1, class 2 means P2. Sir Ronald Fisher, a famous British statistician, was one of the early ones to work on this discrimination problem. It's called linear discriminant function. So he said that, look at this now, this is psi hat of x. Xi of x was mu1 minus mu2 sigma inverse x minus mu1 plus mu2, but we do not know mu1 sigma square. So we replace the population value by the estimates. So this is the estimate of the difference between the mean, this is the estimate of the covariance sample, the pooled covariance that we have already talked about, and so it's the same function. It's a close relative of psi x, is called psi hat x. Assume Ni, the number of samples, please understand the number of samples. So we are assuming that there are a number of samples, right? N1, N1 comes from one class, N2 comes from another class. So, what is that? The large sample theory that we are assuming here. Ni's are greater than D. What is D? D is the dimension of the space in which the vector x exists. So, I want the number of samples to be larger than the dimension of the space, and I am also assuming sigma hat is invertible, because I am going to estimate and I am assuming it is positive definite, hence invertible. Therefore, the error in psi hat is given by that, where x prime and x double prime are samples from P1x and P2x. So, this was called the Fisher's discriminant function for the standard cases. Kolmogorov then revisited this Fisher's analysis in 1960. You know, Kolmogorov is the famous probabilist from Russia. He assumed omega, sigma is I, that means the common variance between the two populations is identity. So, this sigma hat x for the identity covariance matrix takes this particular form, which is very obvious thing, because sigma is identity. So, when we set N1 is equal to N2 and D, so what is that? N1 is equal to N2 means what? I am taking the same number of samples from both the population. D is the dimensionality of the random vectors, and if I let both N1 and D grow to infinity without bounds, such that D over N tends to a constant alpha greater than 0, in which case we can show that mu hat minus mu 2 hat, the norm of that tends to a constant gamma that is greater than 0. Again, you should know these are all coming from large sample theory. Here the number of samples go to infinity, the dimensionality also goes to infinity, but such that the ratio d over n. So, you can, what is n? N is the common value of n1 and n2. So, n is equal to n1 is equal to n2, the common value of n2. As n over as d over n tends to alpha, which is greater than 0, let this quantity tend to a constant, which is gamma. So, Kolmogorov analysis continued. Kolmogorov showed that this error function, see, this is the error function, you all should know, right? This is the error function. This error function is going to be, so in this scaling, what is the scaling? N and D go to infinity, d over n tend to alpha. He showed that error probability that is computed by xi hat of ID tends to phi of minus r square divided by 2 r square plus alpha in probability. Now, what was the earlier result? The earlier result was the earlier result was the error is equal to phi of minus r by 2, that is given by 21. So, that is a classical result. What is the classical result? The classical result holds good when d over n tends to 0. Now, what is the corresponding analog that Kolmogorov did? He said when d over n does not tend to 0, but tends to alpha. Look at that alpha comes in the probability. So, what was the earlier one? The earlier one is phi of minus r square by 2. I am sorry, the earlier one was minus, I want to check that just to make sure that I am on the right track. Yeah, r by 2, that is correct. That is r by 2. So, the previous one was r by 2, but the Kolmogorov now tells you it is phi of minus r square by 2 times r square plus alpha square. When alpha is 0, it reduces to this, but when alpha is greater than 0, this value is different. Please understand, this ratio is less than r by 2. If this ratio is less than r by 2 means what? Error is larger when alpha is 0. Error is larger when alpha is greater than alpha is 0. Why is this? That is because this is the integral under this curve. The integral under this curve becomes increasing with a function of a. A is r by 2, and minus r by 2 comes into play. So, this is a clear demonstration that high dimensional effect leads to suboptimality. Suboptimality. So, this is what we are claiming. When d by n is equal to alpha equal to 0, we get the classical asymptotic result. So, this is a typical introduction to new aspect of analysis of high dimensional problems, new facets of analysis of high dimensional problem. Now, as the last example in high dimension, I am going to talk about the covariance estimation, the effect of high dimension in covariance estimation. Let x1, x2, xn be IID samples from a distribution with 0 mean, where xi's are d-dimensional random vectors. So, we have n points chosen at random in RD. If n points are chosen at random, I have a data matrix which is equal to d by n. This is 1 to n, this is 1 to d, that is the data matrix. Sample covariance, if the variables are from 0 mean, the sample covariance is essentially given by the estimate, which is sigma hat, which is 1 over n times xx hat, xx transpose, sorry, xx transpose. So, that is the covariance. It can be shown that this is an unbiased estimate. As the number of samples n becomes larger and larger, the population covariance, when d is fixed, the sample covariance converges to the population covariance as n becomes larger and larger. This is the classical convergence result. Now, I am going to talk about the distance between the two matrices. Please understand, omega sigma is the unknown matrix, sigma hat is the estimate of that. I am going to compute the norm of the difference. So, the difference is a matrix. I am going to consider the norm of the difference. I am going to consider the spectral norm. So, the spectral norm is essentially the supremum of the difference between the two matrices acting on U. It can be shown this spectral norm tends 0 as n tends to infinity. That means the sample covariance is strongly consistent estimate of sigma in the classical setting, and that happens when d over n goes to 0. But now come to high dimensional effect. Now, n and d grow, d over n is alpha. So, I am now considering a case of an estimate when d over n is equal to alpha is in between 0 and 1. One way to check the equivalence between two matrices is to compute their eigenvalues. Why? The spectral norm relates to the maximum eigenvalue. I think we have already alluded to when we talked about matrices and norms of matrices. So, if you compute the eigenstructure of the original matrix and the eigenstructure of its estimate, we can talk about measuring the difference between the estimate and the original matrix. So, let lambda 1, lambda 2, lambda d be the d eigenvalues of the d by d matrix xx hat, I am sorry, xx transpose. Of course, there is a 1 over n the normalizing constant comes into play. So, lambda 1 be the maximum, lambda d be the minimum. I am assuming the minimum is also greater than 0. Now, I am going to assume a special case when sigma is identity. What does it mean? I am getting samples from a box with n identity. I am going to get a vectors x. Each vector belongs to Rd. I am going to get a set of n samples. I have a matrix x, x1, x2, xn. And now I am going to compute the covariance sigma hat, and sigma is the original one, which is I in this particular case. In this particular case, sigma is equal to I. When sigma is equal to I know all the eigenvalues, they are all unity. When d over n is alpha, so I am now trying to compute the eigenvalues of sigma hat, the eigenvalues of sigma hat, that means estimate of that. It can be verified when n is 4000, d is 800, alpha is equal to 0.2, d over n. D over n, and if you compute the eigenvalues of sigma hat, they are distributed on either side of 1 instead of being 1. Look at that now, they are distributed. This is the histogram of the distribution of the eigenvalues of sigma hat. When you change that to 4000, d is equal to 2000 and alpha is 0.5, again here is 1, there is a distribution of that happens. So, these are empirical distributions of lambdas for alpha is equal to 0.2 and alpha is equal to 0.5, alpha is equal to 0.2 and alpha is equal to 0.5. Please understand, all these values should be equal to 1. When in the high dimension, the eigenvalues are split in between lower as well as higher, the lower as well as higher. For the identity matrix, all the eigenvalues are equal to 1. So, you can see I can measure the error between the estimate and the original matrix through the spectrum, the differences in the spectrum. This property has been analyzed by Russian mathematician Marchenko and Pastor. They, as early as 1967, they talked about the impact of high dimension. This is called Marchenko-Pastor law. They proved that the density of the distribution of lambdas. So please understand, x is random, the lambdas are random. The distribution of the lambdas are in the interval t minimum to t maximum. So, t minimum and t maximum, and t minimum of alpha is 1 minus alpha 1 minus square root of alpha whole square, t maximum is equal to 1 plus square root of alpha r square. So, this is equal to 1 minus square root of alpha square, this is 1 plus square root of alpha square, and here is 1. So, you can really see when alpha is 0, d over n tends to 0, that are classical statistics. The upper bound and the lower bound coincide and becomes 1. So, when d over n is equal to alpha, alpha is not equal to 1, it is a non-classical flavor. The result has a non-classical flavor. So, what does this essentially tells you? This essentially tells you that high dimensional problems are very different intuitively. We talked about the volume of a square, volume of a cube, volume of a sphere, and we talked about sphere inside the cube, cube inside the sphere. We talked about the distances. We talked about the radius of Gaussian. We talked about tail probabilities, and we also talked about two-class discrimination and covariance estimation. All these result together tells you that high dimensional geometry. High dimensional geometry is very different. High dimensional statistics is very different. In high dimensional statistics, we are going to have a non-asymptotic point of view. Non-asymptotic means what? Neither n nor d goes to infinity, but the ratio is not equal to 0. D can be large, n can be large. These kinds of results are beautifully described in a book on high dimensional statistics, a non-asymptotic point of view by Wainwright, 2019. Version 9, High Dimensional Probability Introduction with Application to Data Science. Of course, Hopcroft and Kannan, Foundations of Data Science is a very good book, is available in Indian edition, is very cheap, you can buy one. And there is another book by Schickman and Miller, Foundations of Data Science for Big Data Analysis. That is a very small, very good book. And there is also a book by Wang, which is 2012, about more than 10 years old, but it is still very good book that provides geometric structure of high dimensional data and dimensionality reduction. So, with this I believe I have given you a good idea that big data analytics is different from the classical statistics. We are going to be talking about a non-asymptotic point of view when d and n both large, but d over n is alpha, which is greater than 0. Thank you.